All right, good morning, everyone. Thank you, Bob, for the introduction. I'm Bassem Andraus. I'm a professor. I got actually my full professor promotion 3 years ago, so that was a big relief for me, and I appreciate the introduction. I appreciate the invitation from Rail Tech and the opportunity to talk to you this morning about the presentation. Riley gave a wonderful introduction that will help me significantly in just sailing smoothly through my presentation. The title of the talk I'm going to give today is Prototype Development of Concrete Cross Ties with Adaptive Prestressing System. This is a continuation of a presentation that my student, Minsu, gave last year virtually, and maybe some of you have watched the recording. And we're actually just got granted phase 2 of this project. So this phase 1 that Minsu gave a talk about last year, this is one of those innovative topics that we're still dreaming about, what's the future for cross ties and how we design them, how we pre-stress them, as Riley has indicated. So in the phase 1, we focused on proving the concept, this innovative idea. Now that has been proven. We're now moving to phase 2, where basically we're looking at now building a full-scale prototype and testing it hopefully in the field. So the phase 2 just got granted, so we don't have so much research done yet. So I'm going to actually walk you through what we have so far. Going back to what Riley had said in the first couple of slides, very important, looking at the two critical support conditions that actually result in most of the demands on the cross tie: the center bending, okay, and the rail seat. So basically we have center negative and rail seat positive. So those are the two critical ones that pretty much govern the design of the tie, and that's why we pre-stress it for. However, when you look at the actual way we pre-stress the ties, on the left, we typically have pre-stressing strands or wires, right? They run from one end of the tie to the other, pretty much throughout the entire depth. We pre-strain them, and then we cast the concrete. When the concrete sets, we release the wires. So basically, it applies the pre-stress. Now, the one on the left is basically looking at the pre-stressing globally, meaning that, the level of eccentricity that Riley was talking about, which is basically pre-stressing is nothing more than just P times E, force times eccentricity, right? With this design on the left, we have very, very little room to play within for eccentricity. And I'm going to talk about that later. Now, hypothetically speaking, what if we can switch to the design on the right? And basically, we can target specific locations where we can apply pre-stressing at the center negative, rail seat positive primarily, and then maybe add few pieces here and there as needed. But those are the two main primary locations. Now, that is going to help us tremendously in not only localizing the pre-stress where it's needed the most, but also eliminate pre-stress where it's not needed, like the end region. Problem that Professor Peterman, is going to be talking about, and he had done a lot of research on, is the end splitting cracks. So we can avoid end splitting by not introducing much pre-stressing at the end of the tie, for example. Now, how is this possible? Well, we thought about a new material that we can use that's just emerging, and we can use it for that purpose, to localize the pre-stressing. It's called shape memory alloys, or SMAs. Now, when you look at SMAs, it's like any metal, no different. When you stretch it, it actually elongates permanently. And the key here is that when you heat it up with any method, it actually shrinks back to its original shape. So you think it's permanently formed, but it's not. And that's the beauty about it. Now, the good thing about this is if you hold it back and prevent it from recovering its original shape, it's going to pull back very strongly. That's the recovery stress, or the pre-stress force. So basically, instead of using hydraulic jacking or stressing, we're using temperature. And that gives us great versatility in the design. This video here, I hope it works. We'll see. You see me actually stretching one of those SMA springs excessively, bring it all the way beyond elastic region. And then see what I'm going to do now. I'm bringing a lightener. I don't smoke, but I keep it in my office just in case I want to shoot a video like this. And then, I heat it up. It came back to its original shape. And we can repeat this hundreds of times and still the same spring works. So that's what shape memory alloy is all about. Now, what's the adaptive pre-stressing system, which is the topic here of this presentation? It's APS. Basically, we have a very short fuse, could vary in length, right? Made of this material. You connect it on both sides with high strength steel, the conventional steel that we use for pre-stressing the ties. And we can use different mechanisms for connections, welding or coupler or any other method. Now you enclose the region that you want to apply the pre-stress within inside the sleeve. Now the whole point of the sleeve really is debonding this assembly from the concrete surrounding it, because you want to enable it to move, to shrink, to breathe, in other words, right? Like post-tension, right? So that's the whole point of this. And then at the ends, you see here and there, I'm not sure if you can show here, we don't have a laser pointer, but it's okay. That's the actually bonding region with the concrete at the far end, zone 3 here you can see. And this is where the anchorage is going to be developed. So we don't need like an anchorage plates or anything like that, as we typically need in post-tension. You heat it up, this yellow zone is pre-stressed. Now, going back to phase 1, I'm not going to go through the results of phase 1, but just as a reminder, or for those who haven't seen the presentation from last year, we did prove this concept on small scale ties, 1/3, 1/2 scale. Now, these voids down there should not scare you, because this is not the end design. Actually, this was introduced to be able for us to, I know it's scary, to be able to monitor, the material, but the end product won't be anything like that. We used, as Riley had mentioned, the DICs, technology that we use here very actively and at the University of Illinois, very effectively also, with finite element, and we were able to target or apply compression at the zones where we have aimed at, basically the center negative bending and the rail seat positive. And at the rest of the tie, we don't see much compression going on. So that actually proved our concept. We also did flexural testing, rail seat and center, and shows very good ductility. And that was something also very positive. Now, after phase 1 was completed, we wanted to think a little bit bigger, full scale now. Let's just take this to the full scale. So at the top, drawing here, you see this is a conventional design. At the bottom, this is what we started thinking about. What if we just, eliminate all the steel and just put the pre-stressing where it's needed, as you can see here. But one thing that came to mind is pre-stress losses. Something that's very important. We cannot overlook pre-stress losses when we're dealing with pre-stressed concrete. It was going to happen no matter what. The issue with the conventional pre-stressing method that we use now is because we are coupling together the casting bed with the stressing. Actually, that is the issue, because we have, for production purposes and the turnover, rate, we have to actually produce these ties with certain amount or certain number every day. So we release the wires within a day, 2 or 3 or so, right? The concrete is still fresh, still young, and that actually causes a lot of creep and shrinkage over time, which leads to excessive pre-stress losses. Unfortunately, we cannot avoid that. Otherwise, we have to slow down production, which is not a good thing, of course, right? So you see here the blue curve, that's conventional steel pre-stressing after releasing the wires a couple days from casting. And then the red is the APS. Now the APS, the beauty about it, because we're not using hydraulic jacking or stressing, you can use any mold, not necessarily the one used for pre-stressing, whether it's the carousel or you're using it on it doesn't have to be the cast bed necessarily. And you can apply the pre-stress when it's needed, after a week or 2 or 3 even. And that will, by the time, we apply the pre-stress, the concrete will have matured a little bit, and you see much less creep and shrinkage. And you see, long-term wise, they reach the same level of stress. So that's something that was very important. Again, finite element proved that. So when in the initial stage here on the left, versus on the top versus the after, let's say 1 year, 365 days, you see significant reduction in the conventional pre-stressing of about 23 to 25% reduction in the stress just due to pre-stress losses. Something it's unavoidable unless you use different types of materials and advanced materials, which we don't use currently, unfortunately. And with the APS, we have in the range of 2% or so. So that was very promising result. Now, let's go back to the development of the prototype. There are 4 components that goes into our prototype that we have to test. over the next couple of years. And we just started, so I'm gonna, touch a little bit on a couple of those. The first one is the fuse itself, the SMA. That's the kind of like actuator that engages the whole system, right? What material and what the properties of these materials. The second is the connection, welding versus coupler versus any other method. And then the sleeve or the debonding mechanism of that with the surrounding concrete. And then, of course, at the end, the heating method. Now, that in itself is very, puzzling to us because the fuse is inside the concrete. We don't have direct exposure to it. How are we going to heat it? Okay, so we're actually investigating that as well. Now, when we look at the fuse, in the first phase of the project, we looked at a little bit expensive material made of nickel, titanium, and niobium. This is an expensive alloy, but we wanted to test the concept with it. Now, in this phase, we're also adding a little bit more cost-effective material. This is actually a bar, almost number 5 bar made of this shape memory alloy, but it's actually iron-based. So it's much cheaper. It's now produced primarily in Europe, but we're trying to bring it here to the US as well. But it's fascinating because you see here the properties. Actually, on this curve shows that we stress it to about 6-7% strain, unload, and then lock it in place. And when we heat it up, it actually produces about 40 KSI recovery stress, which is what the pre-stress is. I mean, the pre-stress doesn't seem to be high with the 40 KSI, but when you think about it, with the large diameter, the amount of force we can produce is pretty large, as I'm going to show you later. And after that, we pushed it all the way in tension until it reached failure. So that seemed to be a very promising, actually, fuse for us. And that's what we're investigating right now. When it comes to heating, we examined different methods. And these are all methods, whether the tape or the heat gun, that we cannot use inside the tie, but it helped us understand how the material respond or react to temperature. The bottom line is, once you hit a target temperature of 200 to 250 degrees, that's it. In 2 minutes or so, it reaches its recovery stress. The pre-stress builds up and it never goes away, even when you stop heating it, right? Regardless of the method of heating. So that was a very good thing to know. Now, when we look at both materials, the one we tested in phase 1 of the project versus phase 2, the little bit more expensive one on the left actually give us a little bit high pre-stress 80 KSI, but low modulus, 8,000 KSI. The one on the right, lower pre-stress 40 KSI, but higher modulus, almost like the steel, 29,000 KSI, which is a good thing. So again, each one of them has its own pros and cons. Heating wise, we came up with the idea, well, why not induction heating? This is inside the concrete. I cannot reach it. I need a non-invasive method to heat the thing, right? So induction heating, and maybe many of you are familiar with it, it's used for so many applications in many industries. We thought that this would be a great way of doing it. The device we use here, equipment in our lab, in the Talbot lab here, a neighboring lab here to Newmark, has an output power of about 5 kilowatt. And we did some testing to see the effect of the cover of the concrete on the amount of heat we can introduce to the material. So basically, the cover you can see from 0.5-inch cover to 1.5, and you see a big change in the amount of heat. So we can heat it up to about maybe 370 or so degrees Celsius. We don't need that high. As I said, all what we need is about 200 to 250 degrees for about a minute or two, and you are good to go. So imagine these cross ties sitting on the ground. It doesn't have to be in the mold, to be demolded, and there are a bunch of them, and you have this portable induction system, and you go and heat just where the fuse is at. That will engage the pre-stressing right away. And this could be done anytime after you are done with the demolding, right? So that's something that we are also investigating. Now, we looked at the design. How do we want the design of the pre-stressing system would be? So we looked at various options, the pre-tensioning versus post-tensioning. And we looked actually at, for example, pre-tensioning. One thing you notice here on the left for the reference tie, when it's pre-tensioned, this E, that again, going back to what Riley was talking about, this eccentricity at most is between 0.2 to 0.5 inch. Very little room, for you to move within. However, now, because we don't have this issue of hydraulic jacking, we can actually afford going with 2 times, 3 times, or even 4 times that eccentricity. And we can have different designs, straight versus parabolic. So I'll give you an example here with this. The top one is the conventional tie. The middle one, we have this APS, but in form of straight. We use it here like rebars, but they are pre-stressed rebars with the end hooks and everything, right? And they are localized where we need them. Center negative, rail seat positive. Remember, this is our target area. We also tried the profile of having it a parabolic. So rather than having 3 fuses or locations for the fuses, we have one longer fuse in the middle, and it can engage this. We see this a lot in bridges, by the way. So those who have seen bridges design, this concept is used in bridges. And I don't see why now with this we cannot use it in ties. Now, the good thing about it, if you notice here, one of the reasons for the high depth of the rail seat region in the tie is that we want to create some room for the shoulder inserts in the tie. Now, that's not going to be an issue anymore if you use the parabolic profile, because simply we are able actually to, have large eccentricity there, no interference of the reinforcement with the shoulder inserts. So that's another additional thing. And we save material here also, concrete, about 10% reduction in the concrete. That's one of the designs. So we did finite element analysis, of course, using Abacus, and we modeled the SMA as truss element, and we have that some portions of the tie it's bonded, and other portions it's unbonded. And basically, we started looking at something like this. This is what the ARIMA test would look like, required ARIMA test for the rail seat positive, center negative, and we mimic that with finite element. So, for example, in the parabolic design, I'm showing here the results, both pass the ARIMA requirement. So the point here is that we're trying to show that with this APS design, we can meet the ARIMA requirements with full scale. It's not that we cannot. So that's the thing that we wanted to demonstrate. Looking at post-tensioning, the same thing. I'm not going to reveal any of the details of the designs that we got from companies or who's the manufacturer is, but the bottom line is that the eccentricity there is very small with post-tensioning systems that we currently use. We can actually try to expand that. So once the E goes up, P goes down. P times E is the moment. Remember, E goes up, P goes down. P goes down means less steel. And that's the beauty of this. So here, for example, we're using this fuse of the 15.8 or number 5 bar, connecting it with 12 millimeter diameter steel, high strength steel. And we varied that from 12 to 8 millimeter. And then we see different results. One of the parameters actually we have was the length of the fuse, 17, 12, 6 versus the length of the steel. This ratio plays a big role. The longer the fuse, the more pre-stress force we get. And that's expected. We have a longer fuse, it has more deformation, it can pull more of the steel, produce higher pre-stress force. And you see there, right there, the reduction in the steel, significant reduction in the steel with using this that could actually exceed 50%. Again, I'm throwing ideas at you that we're still thinking about. And by the way, by the end of this presentation, I would appreciate really if any of you would contact me or email me with any ideas based on this presentation that you can think of that you would like to see in the prototype, for example, because this is still work in development. We also looked at the eccentricity as another parameter there, which is basically from the top to the bottom of this whole profile. We varied that and we looked at how much difference it makes. And we found that, in some cases, it satisfies all 4 sections because we're looking at the 2 critical ones, which is the ones we have here, the center negative and the rail seat positive. These are all the cases we studied. Basically, you see the APS length, the fuse length varies from 12 to 34 inch. The diameter varies of the steel from 12 to 8 millimeter, and they all meet the ARIMA requirements. It's just a matter of efficiency and the amount of material and how much reduction. So it's a very versatile, if you will, design. Last slide here before I conclude is when you look at other sections. So yes, we know that center negative and rail seat positive are the critical ones, but how about rail seat negative and center positive? We also want to satisfy the ARIMA requirements. However, that's something maybe I would like to get your feedback about. Should they have the same demand, these sections, rail seat positive and negative, and center negative and positive, or should they be different? Again, that's something that's we can debate later. But my point is that we satisfied all the ARIMA requirements. So this work still in development, but I would like to conclude and say that It's well known that with the post-tensioning or pre-tensioning that we use right now, we have very little room for eccentricity. Does not exceed by much 0.5 inch. Now we see that we can actually use as high as a couple inches of eccentricity with the APS, which help reduce the amount of steel. Another thing is that the pre-stressing in the center region and the rail seat region, they are decoupled. Here we cannot decouple. In the conventional system, they are related because the same wire goes from one end to the other. It affects both regions. Here you can apply pre-stressing at the center, pre-stressing at the rail seat without any, problem with that. Pre-stress losses, actually that's an important thing because we're able to reduce it by decoupling the casting bed from the pre-stressing system itself. Reduction in material, we saw from this analysis about 50% reduction in the steel, about 10% reduction in the concrete. And of course, whether we use the more expensive or the less expensive alloys, it doesn't matter because the results at the end is just P times E. Again, that's the important thing that I want to leave you with. I would like actually to acknowledge the effort of my students, Minsu Sung and Ernesto Perez, who provided all of the results actually in this slide. I also would like to acknowledge the support provided for this research through the Rail Safety Idea Program, project number 46. And I'd like to also thank the external review panel assigned, and by the Idea Program. Again, we have a couple of them here, Dr. Rex Konahi, Mr. Jim Fabinski, Mr. Vince Peterson, and Mr. Brad Kirchhoff. I appreciate it very much. Also, special thanks to Boslo in America here, Mr. Logan Limmertz, for his help actually in providing us with the design plans for pre-tension and post-tension tie that we actually based our ideas on. So, and they also offered to help us with the casting and construction production of the final full-scale prototype at their facilities. So we really appreciate their help with that. With that, I would like to thank you all, and I will be more than happy to answer any questions. This is my email, by the way. Unfortunately, I have to run for a field test because of miscommunication. I scheduled the test today, but if you have any question or anything, please reach out to me, and I'll be more than happy to discuss any ideas you have, because this is still work in development. It's very early. We can do any idea you can come up with. Thank you again so much, and I'll be more happy to answer any question if we have time. Thank you. Question in the back, yes.
Have you measured your camber with increasing
The camber, we have not. We have not measured the camber, but we're not expecting, a lot of change. Well, the pre-stress losses will affect the camber. That's a question that probably we will do that with the full-scale prototype, but we have not done any full-scale measurements of that yet. But that's a good point. Thank you. Yes, another question.
As far as this, the forces that y'all are putting on the path, are you seeing it stress that fuse back out where it's going to have to be reheated ever so often?
That's a good question. Creep of the fuse, this material actually has great creep performance, and we studied that on different projects, but it has great creep and relaxation performance. So meaning that it does not lose its stress. The only thing that would affect it is temperature, meaning that depending on the alloy we use, if the temperature drops down significantly, like I'm talking about like negative 30 or 40 degrees Celsius, which is really unlikely to happen, that's when you start seeing it actually loosening up and losing its pre-stress. However, coming back to your point of reheating, that's one of the advantages that maybe I missed here, that yes, if you see, for example, a crack or some kind of issue with the tie and you heat this again, it's going to re-engage it like brand new. So that's an advantage, another advantage that appreciate you mentioning that. Right, thank you.